Hi class, I want to open this video with a question. Does a liquid sample evaporate below its boiling point? Well, have you ever come across a puddle and a few days later the puddle's gone? What happened to that liquid? Where did it go? Well, it evaporated. It transitioned from a liquid to a gas. And how does that process happen if a substance is not boiling? The idea is related to vapor pressure. The vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid or solid phase. So what does that mean in simple terms? Well, if we have a liquid, some of those molecules have enough energy to escape to the gas phase, right? In order to evaporate, there must be enough kinetic energy to overcome the intermolecular forces present between those liquid molecules. So there's a small fraction of molecules within the liquid at the surface that have enough kinetic energy to escape to the vapor phase. And those vapor molecules exert a pressure. So pressure is a force per unit area. So Newton is a unit of force, and meter squared is a unit of area. And we're just going to talk generically about pressure right now, but there is pressure all around us, and this pressure is caused by molecular collisions. So molecules in the gas phase cause atmospheric pressure. So we've probably heard of that. When we see the weather, we see areas of high pressure and low pressure, and that's related to the collisions of air molecules around us, exerting some pressure. We can also think about pressure exerted within, say, a balloon. The molecules within the balloon are exerting some pressure that's great enough to hold that balloon's shape. So vapor pressure relates the amount of force that the vapor molecules above that liquid or solid are exerting on a container or the atmosphere. Let's take a look at this flask filled with a liquid. If we evacuate the space above the flask with a vacuum, now this is empty space. This empty space will begin to be filled with vapor molecules. So some of those molecules in the liquid will have enough energy to escape that liquid phase and transition to the gas phase. And the amount of pressure exerted by these vapor molecules is what is defined as vapor pressure. And we can see that the mercury in that U has been moved once those molecules evaporate, and that is how we measure vapor pressure of liquids. Volatility is related to vapor pressure. The more volatile a compound is, the higher the vapor pressure. Volatility describes the tendency of a substance to evaporate. So if a substance vaporizes more easily, it's more volatile. It will exert a higher vapor pressure because there's going to be more molecules causing more of these collisions. Now let's use some concepts of kinetic molecular theory to explain trends in vapor pressure. Kinetic molecular theory, as you recall, tells us that molecules are in constant motion and that the temperature of a sample is proportional to the kinetic energy of that sample. So at higher temperatures, we have more molecular movement, therefore we have more kinetic energy. And if we take a look at this plot, this is a distribution function that shows us the fraction of molecules that have a certain amount of kinetic energy. So let's say this is at room temperature. At room temperature, we have a large fraction having somewhat small kinetic energy. But there is a spectrum here, right? There are some molecules, a small amount of molecules that have high kinetic energy. And just like a classroom full of students, right? There might be a distribution function of energies there. Some are sleeping, they have very little kinetic energy. Some are wide awake and really excited and intrigued by the lecture topic that day. And those have a lot of kinetic energy maybe. But most of the students are just happy to be there, sitting there taking notes, and they have an average amount of kinetic energy. Let's define a point on this x-axis where there is sufficient kinetic energy to evaporate. So above this threshold, these molecules have enough kinetic energy to evaporate. So if they're near the surface, they will. Okay? Now, if we shift the temperature to a higher temperature, what does this curve look like now? Well, it's shifted to higher kinetic energies. So a large number of molecules still have a lower amount of kinetic energy, but there is a larger fraction now that have a high kinetic energy, and a larger fraction above that threshold to evaporate. So at higher temperatures, more molecules can evaporate. So more molecules evaporating, higher pressures. So as temperature increases, vapor pressure will increase as well. This plot shown here highlights the relationship of vapor pressure and temperature. So we have vapor pressure in units of ATM on the y-axis and temperature on the x-axis in Kelvin. I'll take a second now to remind you that the temperature in Kelvin can be related to degrees Celsius by taking the temperature in degrees Celsius and adding 273.15. So as temperature increases, the vapor pressure increases. We can see that on each individual curve. Each curve here represents a different compound. So what determines the vapor pressure for a given substance? Well, the same thing that determines melting point, boiling point. Intermolecular forces. Intermolecular forces, remember, attract molecules to one another. So in order to escape the liquid and transition to a gas and exert that vapor, they must have the ability to overcome those intermolecular forces. So if they're held more tightly, so strong intermolecular forces, there's going to be fewer able to escape the vapor phase and therefore a lower pressure. So as we have stronger intermolecular forces, the vapor pressure decreases. And the opposite is true as well. So as the intermolecular forces in a series of compounds decreases, then the vapor pressure will increase. We can also gain some other information from this plot. A substance will boil when the vapor pressure is equal to the atmospheric pressure. So standard atmospheric pressure is 1 atm. So we can find a substance boiling point by looking for the temperature at 1 atm, because when the vapor pressure is 1 atm, equivalent to the atmospheric pressure, the substance will boil. So take, for example, water. At 1 atm, the temperature is 373 Kelvin, approximately. And that corresponds to the boiling point of 100 degrees Celsius. We can also see from this plot that at the same pressure of 1 atm, iodine has a much higher boiling point. So by looking at this plot, we can see that molecules on the right-hand side have higher boiling points and therefore would have higher intermolecular forces compared to molecules on the left-hand side. You may want to take a couple minutes and look at this plot to make sure that you can understand how to read it. This plot also allows us to see what would happen to the boiling point at lower pressures. So let's say we are in Denver at higher elevations and the atmospheric pressure is only 0.8 atm. Well, now what happens to the boiling point of water? Well, find 0.8 atm on the plot, go over to water's curve, and go down the axis. Well, now the temperature is lower than 373 Kelvin, and that's what we observe. At higher elevations, the boiling point is lower for compounds. And this is due to the fact that the pressure is lower, so there is less energy needed to evaporate. The lower boiling temperature means that we need longer cooking times because the temperature is now less. We need to cook it longer to reach the same level of doneness as we would at a higher temperature. I appreciate you tuning in for this video on vapor pressure, where we talked about the definition and how vapor pressure is related to the temperature and the strength of intermolecular forces. Thank you for watching.